Hello, Paul Russo here to explain to you the use of the SMALS MultiRun program. Multi-run is what you do if you have data that are very hard to clean up. So for example, you have a sample that had a lot of dust and there's really nothing you can do about it at this point in your life. Best thing, of course, is to have perfectly clean samples, in which case you would use just one run and our program harvest. Multi-run is not a bad idea, though, even if you have a clean run, because it has some features that we find likable. For example, it contains a nonlinear least squares version of cumulance fitting. So let's go ahead and start. What you do in this program is you put a clean version of the SMALS MultiRun program with no data in it into your directory that contains your multiple runs. In this case, there are 10 runs of a latex that's supposed to be a 50 nanometer latex, a pretty small latex. I think it's pretty dilute as well. And it's definitely noisy because we didn't do a lot to clean it up. In fact, I think this is really just a very old sample that we pulled off the shelf just to demonstrate. So you go ahead and launch this program. And it might come up saying that you need to enable some macros. And if it does, just enable them. This doesn't on my computer since I run it a lot. It seems to know that it's not needed to ask me that. So by default, this Choose Files menu appears. Before you actually do that, you want to look down here in the sort of the tray where all the tabs are and see if there's data there. If there's data there, you'll see more after this gamma versus q squared tab, which is useless, by the way. It's a remnant of an older program. You will look here and see if there's any data. If there is, you can go ahead and delete it. It's not a big deal. I'll show you how to do that. But if there is something there, you would close this menu and click Clear Sheets. Let's just be absolutely sure. So now it's going to clear everything. Fine. So when in doubt, clear. Now you can redisplay the naming form. And we'll let this one come in, and we'll take in all of the 10 runs. And we do that by pressing Shift and click on the bottom one. Click the top one, plus Shift and click the bottom one, just like normal. And it will go ahead and open them. It'll take it a while to do this, and it doesn't look pretty while it's happening. You can follow along, sort of. Oh, there was a bad one. You see the intensity plot there, bad. But they're usually coming in a little fast to really carefully analyze. So we'll go back and look at them individually later. And you see each time one comes in, you get a new tab down here where all those data are held. So most of them look pretty bad, right? All right, so now 10 looks okay. So go to the left here and scroll back to the first one, and let's have a look at it. Well, things seem to be going along pretty well until at the very end. I don't know why it's always at the end. It isn't. You get this giant spike on the lowest angle. These colors do not correspond to the ALV colors. Later in the program, they will. But anyway, we know that's the lowest scattering angle. It's the most likely one to have a dust issue. And let's look at the effects of this giant spike. It raises the baseline. And that's true in all 4 plots. Notice we have all the 4 plots that we like. Log ln, ln log, and log log. We have all the 4 plots. It messes up semi-log, but messes them all up when you have something that serious. So we know we're not going to keep that. We'll just keep a mental note. 1 is definitely out. 2 is better than 1. The effects are less dramatic, but they're still there. We still have this baseline lift off here. We have a flattening in the semi-log plot. So 2's bad. 3's bad. Only 1 does spike now. It's not as bad. In a pinch, I might be tempted to use it and then maybe just not use that lowest angle, but I don't think we'll need to do that here. We'll eliminate it. 4 looks decent. Actually, if anything, that looks like I got slightly hit on the second lowest angle, but I'm going to say 4 is a keeper. So now I have to click over here to advance. I don't know. So flattening there. I guess I'll kill 5. 6. Mess. 7. Oh, we got lucky. So far it's 4 and 7. 8, disaster at the beginning. Disaster on 9. We're going to say 10 is a keeper. So it's 4, 7, and 10. All right, so what we do in this program, it's not the most elegant thing you could imagine, but it works. We're going to clear that. And you get these warnings. Don't worry about the warnings about negative numbers on log charts. And redisplay the naming form. Choose files. This time we'll hold the control key and we'll pick 4, 7, and 10, just those 3, and see what we get out of those. So we already inspected them, so there's no need to inspect them further at this point. Okay, so what we'll do is we go back to main. And actually now is a good idea to, before we do that, let's check that we have our parameters right. Yes. Okay, this is important to have your parameters right. Really should have done that at the beginning. Go to main and have it compute the averages by clicking that. And it gives you this information thing. The maximum lag time it's displaying is 5 milliseconds and change. And there's the result. Okay. Well, let's see, we can get them all 4 on one screen here and look at them a little bit. They look okay. Notice that here we have one really seriously errant detector. And we're going to have to eliminate something like 1, 2, 3, 4, 5, 6, 7, 10. Maybe the first 15 points will be eliminated, at least for that detector, but really there's no reason not to eliminate points lower than that for any of the detectors. But otherwise, it's okay. I mean, there's a little flattening here at the end, but that's, 1, 2, 3, 2.5, 2 and change. Powers of 10 before that's happening. It looks basically okay for such short runs. So the next thing that you have to do is populate export sheet. Now, maybe you don't plan to export the data to some other program to make it beautiful. But even so, you have to click this to do further analysis because the further analysis grabs the data from that for export sheet. All right, so let's go ahead and do multi-exponential fitting. And the equation that we're fitting is shown here. And what we're going to do is, by default, I think it'll come in just fitting a baseline offset, amplitude, and decay rate. If you want to fit more than that, you can do it. You can do that by going to Data, Solver, and adding other cells to fit. So you see here, we're fitting base adjust, amp1, and gamma 1. These are the cells that are right here in the screen zone. Green means enter a number in my software. Green to go to enter a number. And you could add additional parameters right there for amplitude 2, 2, 3, 3. So you could add them, but there's no reason to do it. And of course, we're minimizing the target cell, which is going to be this thing here, the sum squared of errors in H11. So it all makes sense if you're used to using solver. So we'll close this. We're not going to do that. What we're going to do is designed to slow you down. You could go ahead and just fit all of them at once, and then you'd have a big mess. But it's designed to make you look and think. Let's boost the number of channels that reduce the number of channels that we're fitting. We'll go from 15 to 128. You're floating a baseline, so it's not really critical how many channels that you use in a nonlinear least squares fit. That's kind of nice things about it. All right, so load angle 1. Load angle. And goes the solver. We click OK. It's OK. And there, it's provided the data that it loaded. The vertical bars show the range of the data that we fit. And you don't see a very good view of the residuals here for two reasons. One, they're probably pretty good. Two, we're plotting everything, even the ones outside of the fit. So if we really wanted to see how well these were working in here, we could go in and just plot the residuals by clicking and checking. But they're pretty good in this case. Let's see, load angle 2. Load angle 3. Looks good, but notice there's some missing here. Some data seem to be missing. Those probably went less than 0. That's okay. After the baselines fit, it draws some above and some below. Be nice if it wasn't so systematic, but what can you do? Okay. This is our bad one, bad channel. Let's see what these residuals look like. A mess, see? But we pretty much got it tamed by the time we're fitting the data. Maybe we could have gone higher. Okay. And 7. And 8. So the design of this program is that it's kind of wide. So in order to see what's going on, you kind of have to scroll over here and see what it's doing for you. And it's doing some nice things. Here's our gamma versus q squared plot. And notice that it looks pretty decent. I've seen worse. Okay. And remember, we started with total garbage as data. We only could pick 3 runs, but the 3 that we selected were okay. So in theory here, we could draw a line across that and get the, extrapolated 0Q diffusion constant. And we could do the same here for a radius. Let's actually just get that as an average here. And let's get the standard deviation of those as well. And let's get the percent standard deviation. I sort of like to have that. So it says 28 plus or minus 1.6%. Well, the right answer was supposed to be 0.05, but microns, so that'd be 50, and we're getting more like 54 when we double, closer to 55, huh? 55.4 maybe. So actually, that's probably pretty good. I don't think that there's any reason to trust the vendors more than we trust ourselves on these things. If you wanted to corroborate this, you could do some other methods. This would be a little bit difficult to do by static light scattering the sky, but you could do it on X-ray scattering or something like that. So anyway, that's the use of the program insofar as the multi-exponential fits go. Cumulants is similar deal. It shows the equation that we're using. Again, you use solver to adjust how many terms you want in the fit. I think this is currently set up to do second order cumulants fit. But let's see how that works, see if we get the same kind of answers. And here I am being a little restrictive on channels to use, okay, because it's cumulants. But I think actually in this nonlinear least squares fit, I wouldn't have to be. I think I would get pretty much decent answers anyway. Did I do that already? Yeah, that's a good point I should mention. You'll see some data that are in here. The clear routine doesn't monkey with the cumulants fit, but it reloads it. So you'll have to be sure that you click every angle here. Interesting. Here we have a little bit indication of slight problems with the sample, maybe. So a little bit of tilt to these D-app versus and R-app versus Q. But you can see that the intercept is within there of what we had before. Up to you whether you think that's a flat line or curvy line. Pretty low correlation coefficients on those, as you expect. So it's important also to look here. You may get some hints as to what's going on because we plot the PDI parameter, mu 2 over gamma of r squared, as a function of angle. And you may see a little bit of a upturn here at the low angles, indicating some problems within. And if that was the case, you could actually decide, well, there's something going on here. Maybe I shouldn't use all these points. So it's kind of up to you, as always, the user, but you see that in any case, you have taken a really crappy data set and turned it into something useful. I like to say these as something. So let's call it multi-run completed. And that should be the end of the video, I think.